Well, if I was ever set up to fail, that was it. Okay, so yeah, what I'd like to talk to you about tonight is antimatter. And it's quite often talked about in things like science fiction. I'd like to try and show you how it actually is a perfectly real thing, a perfectly practical thing, and in fact something that I use in my professional life every day. But let's come to some of the uses, in fact, that you may encounter in your life. In fact, one of them I hope you don't, but if you do need it, you'll probably be quite grateful for it. So most of us encounter the idea of antimatter at one time or another, usually through science fiction. Probably the earliest one I encountered it with was Star Trek. If you remember, the Starship Enterprise is powered by dilithium crystals, which by some miraculous means they managed to capture antimatter in some crystal and use the antimatter to power all of the spaceships. My favourite is Doctor Who, and I had to get this in given it's got its 50th anniversary coming up next week. But you know, the Doctors keep on encountering antimatter all the time. This is way back at the 10th anniversary. This is when the second and the third Doctor encounter a character called Omega, who gave power to all the Time Lords and allowed them to travel in time. He did that using black holes, which would be the subject of another talk. But in doing all of that, he managed to blow himself into an antimatter universe, which was kind of unfortunate. And in fact, the second Doctor and third Doctor used some of the properties of antimatter to escape from this by basically introducing a piece of matter into the antimatter universe, which had some rather unfortunate consequences. There's also a Tom Baker story here where he comes to a planet and there is an antimatter creature that starts menacing him, which is quite convenient really, because it's mainly invisible, but which is great for the effects budget, but was quite an interesting story. That's a thing called Planet of Evil. And then, of course, and this one it pains me to mention, but there's also antimatter at the heart of the film and the book Angels and Demons. I don't know if any of you actually saw the film or read the book. I'm still recovering from the experience. I watched the first 5 minutes of the film again the other day just to remind myself and point out to somebody all the real bits that were filmed around the Atlas experiment which I worked on. But the rest of the film I found pretty painful. But the conceit was that somehow this group go to CERN where we're making antimatter, which we are. They managed to capture the antimatter, take it to the Vatican, and they're going to use it to blow up the Vatican. Quite why, I can't remember. I think actually while watching it, I couldn't work out why either, but there you go. But I have to acknowledge Angels and Demons and the movie makers, because some of the pictures I have came from them, and so I have to abase myself before them because of copyright reasons. But after all of that science fiction, antimatter is perfectly real. It's produced all of the time in experiments such as the one I work on, but it also poses some pretty big questions about the nature of the universe that we live in. Basically, we're going to come to the question, how can we end up living in a universe that looks like the one that we're in right now? This room shouldn't exist, according to a lot that we know. Antimatter, we can be proud, was a British not invention, but suggestion. It was first proposed by a British physicist called Paul Dirac in 1931. And Paul Dirac had been trying to unite two of the biggest ideas in 20th century physics into one framework. And those two big ideas are those of quantum mechanics and relativity. So I'm just going to take a little moment, basically one slide, to tell you about quantum mechanics and another slide to tell you about relativity. So clearly you're not going to know too much about it at the end of that, but I hope I can capture the essence. So for relativity, it was at the end of the 19th century, in quite a classic experiment, it was discovered that the speed of light doesn't depend on how you observe it. You can be stationary, you can be rushing towards the source, you can be rushing away from the source, but the light you see from that source always appears to travel at the same speed. It doesn't matter how fast you are moving relative to the source. Now that's counterintuitive. That isn't what you would expect from somebody throwing a ball towards you, but that is just experimental fact, and it's been established for well over a century. I put a little asterisk on there because that is, despite the stories that you've You may have heard about faster than light neutrinos. That story went away for perfectly good reasons you could ask me about after I finish the talk and we have the questions. But there are some very big consequences to that, and that brings us to Einstein, who realized that all of the structure of physics that had been set up by Galileo and by Newton and had stood for 300 odd years actually needed updating. And the conclusion you get from that, and you could spend ages on this, it's fascinating stuff, but the apparent passage of time depends on your relative speed. If you see something moving past you at a very high speed, it appears to be aging more slowly. A clock going past you at near to the speed of light appears to run slowly. And light can be bent by gravity. That's another consequence that comes out of this. This is a consequence of general relativity. That seems a bit bizarre, but it was confirmed again. I'm not really trying to push the British agenda, but it was actually confirmed by a British astronomer, Arthur Eddington, in 1920, though the observations he made of the eclipse where he confirmed it was in 1919, where he saw that the positions of a star seen just past the edge of the limb of the sun in an eclipse had actually moved relative to where you would expect it to be because of the gravitational effect of the sun. The light was being bent around the sun. Okay. And then another consequence of this is that of the relativity is that energy and matter convert into each other, and that energy is in some sense equivalent to mass, and you can relate the energy in a given bit of mass by E equals mc squared, where c is the speed of light, and you can convert those two. The thing about relativity is it tends to be important at large scales, whereas you don't tend to have to deal with it so much on the very small scales. Then the other big idea is quantum mechanics. And at the start of the 20th century, people started to realize that unlike the older idea where things like energy could take any value you like, it turns out that things like energy come in chunks. They're quantized. That photons can only have certain definite energies, that if you look at the energy levels of electrons going around an atom, when they jump from one energy state to another, they jump in discrete amounts to discrete levels. They don't just take any old value that they like, they're confined to discrete amounts. And that has many, many strange consequences. They realized that some of the odd behavior of light that they've seen implied that energy had to be quantized and could take some values and others. More work showed that you have other things that are quantized. Even the way that things move, in some sense, if things are spinning around, quantum mechanical, microscopic spinning tops can only spin in distinct chunks of a thing called angular momentum. They can't just spin any old way, they come in distinct chunks. Another consequence of all this, it turns out that particles can behave like waves, and waves can behave like particles. It depends what they're doing and how you look at them, what sort of behavior they express. Many things that you can measure, it turns out, don't actually have a value until you've measured them. This is quite bizarre. There are philosophical implications of this that people are still trying to work out. But this is very big stuff. And these things, when you put them together, lead to what you may have heard of as the uncertainty principles, which says that, for instance, the better you know where a particle is, the less well you know loosely how fast it's going, strictly what its momentum is. There is an uncertainty. The better you know its momentum, the less well you know where an object is. So there's lots of ideas. This little joke here is, Heisenberg, here lies Heisenberg. Well, maybe. Okay. The point about quantum mechanics is it tends to be important at very small scales or low temperatures, though not always. If you go up to the physics department to where our condensed matter people work, you can actually see quantum mechanical effects going on in things which are the size of a bucket. You can have quantum states which are bucket sized, which is quite impressive. Most people tend to think of this as just being microscopic. It's not strictly true. The other thing point I'd make is this uncertainty principle actually is associated with some of the most precise things that we can predict in physics. So this uncertainty is a statement about a fundamental uncertainty, but it's not to say that the theory is inaccurate. It's actually very, very predictive, but it predicts its own limits. It knows that there are limits to what you can measure. So what's this got to do with antimatter? I mean, I've just tried to give you 20th century physics in 2 slides. Well, the point was that people can write down a theory for relativity and they can write down a theory for quantum mechanics. But people then tried to say, well, these things are all operating in the same world on the same objects, just looking at different scales. You should be able to write something down which obeys both quantum mechanics and relativity. And Paul Dirac was one of many people who tried to do that. The only trouble is when you try and put those two things together, you get really weird solutions. Not least, you always end up with solutions that look like the particles have got negative energy. And people basically said, well, we've obviously done that wrong. That's just rubbish. What does negative energy mean? The genius of Paul Dirac was to say, what that's telling you is that there are different states of matter that you're not encountering every day. That these negative energy solutions actually correspond to a different form of matter called antimatter. Interestingly, at the same time, it also predicted some very strange behaviors which are to do with the way that little quantum mechanical objects spin, which had been discovered experimentally, but people didn't understand. And that actually fell naturally out of putting these two theories together. So it's a real double win here. He'd explained something experimental and made a new prediction, which frankly, this prediction of antimatter, a lot of very serious physicists didn't believe. So what's the idea behind this? Well, Paul Dirac realized that you can have a whole ladder of energy states. You can have low energy, higher energy, very high energy, going up like this. There's a whole ladder of energy states. But what the equations were telling him was that there's a whole load of other energy states which are going down below the floor, if you like, to even lower energy states. And what does that correspond to? Well, what he realized was if you pumped energy into a system, had something in one of these low energy states, it would be promoted in energy and would appear as a high energy state, and it would leave a hole. And what does the hole look like? Well, I'm going to give a little analogy here, if I can make this mouse thing work. Oh! And not, here we go. Go on, move. You may have seen this little optical illusion. It's a well-known physicist's face, and it's, in one sense, it's like a life mask, so it's positive, but also, if you look at the back of it, it looks as if it's positive again. So the hole can look like the thing that protrudes out. This is an analogy. What Dirac realized is, where you leave a hole in these states down here, it has properties that look like the thing that you've got left up here, that you've promoted it to, but many of them reversed, like the charge and so on. You have an object which looks like the anti-object to the thing that you've raised up here. This is an antimatter state. This is a positive matter state. It's like the inverse. It's like the hole that's been left. Now, actually, in modern particle physics and quantum mechanics, we have a slightly more subtle view of these things, which frankly sounds more insane, but we believe is more correct. So Richard Feynman, who probably not so well known by the younger people nowadays unless they're doing physics, but older people may remember did lots of public understanding of science far better than I do on the television and things. He and a guy called Stuckelberg reinterpreted a lot of quantum mechanics, and he realized that these antimatter states are actually even weirder. They basically look like ordinary matter, but just going backwards in time. Okay? I expect a laugh at that point, but it's true. Okay? Now, the weird thing is, okay, this is a crazy theory. People like Niels Bohr, who's one of the great figures of modern physics, said, this is just rubbish. This man is insane. Interestingly, this was predicted in 1931. Carl Anderson went back and looked at some stuff that he'd published the year before, looking at cosmic rays. And he'd seen this strange business of two particles suddenly appearing apparently out of nothing, actually produced by a particle of light, which then converts into two particles. This is in a magnetic field, so you can tell what the charge of the thing is, the electric charge, by the way it bends in that magnetic field, and you can tell what mass it was, and you can work out one of them is an electron. And the other thing has exactly the same mass but is bending in the opposite direction. It's a thing that looks like an electron but with the wrong charge. It's an anti-electron, which we also call a positron. He'd actually already observed antimatter and he hadn't realized it. So this stuff is real. Okay, so what are its properties? Well, the most famous one you've probably already heard of. You can do the reverse. I just told you about pumping some energy in, leaving a hole, creating a hole which is the antimatter, and raising something up to a matter state. What happens if you take an antimatter state and a matter state and put them back together again? Well, the previous thing, I put energy in. If you do the opposite, you get the energy out. You get the energy, in fact, that corresponds to the mass of the two objects times the speed of light squared. Use E equals mc squared, you actually get quite a lot of energy out. These two things annihilate each other. If you like, the matter particle fills the hole that is the antimatter particle, and the energy that's the difference in their energy states gets liberated. And that's calculated through E equals mc squared. So there's a huge potential amount of energy that you can release that way. Well, what's that got to do with what I do every day? Well, I work at CERN in Geneva. Haven't been there for ages. I was there last week and I've got to go there for a day on Friday. CERN hosts the world's highest energy particle accelerator, the Large Hadron Collider, which is basically goes through this very large tunnel. You can't see it on the surface. This is drawn on the map. It's actually between 50 and 100 meters underground. This is 27 kilometers in circumference. Oops. Under the area near Geneva. This is Lake Geneva. This is the airport. You can see the landing strip of the airport. The Swiss-French border runs through here. This is the rise of the Jura Mountains to the north. The Alps are over that way. You guys are down in the Prealp. You're probably having a nice time skiing at some of the resorts there. And if you're interested and you're ever dropping by, I've got a flat just over here, which is quite nice. Okay. So, the Large Hadron Collider, as I say, is at CERN. This is actually a truer picture with the accelerator underground. The main site is over here, and just outside the main site and underground is the ATLAS experiment where all my stuff goes on. There's a sister experiment way on the opposite side of the ring called CMS, a similar sized team. There's a team of 3,000 people working here, a team of about another 3,000 people working on this thing over here, and then there are some other smaller experiments which are interesting in their own right. Say it's about 100 meters underground on average. It's tilted at 1 degree towards the lake for one very simple reason. You tend to get water coming through that rock that you've tunneled into, and you don't want it to just hang around. So we tilted the whole 27 kilometer thing at 1 degree so it drains in one direction and you can pump it out. As I say, 27 kilometers around, and what we're doing at the moment is taking protons to the highest energies that we can and circulating them in opposite directions to each other, and then at various points colliding those protons. And with all the energy they have, those collisions can produce new particles. Okay? The ATLAS experiment sits underneath point 1 here, way underground. You see it there. The actual accelerator is quite fascinating. It's colder than the temperature of free space. It's actually colder than the cosmic microwave background. It's even closer to absolute zero. And each octant, each eighth of that accelerator is the largest superconducting system in the world. It's actually quite a fantastic technological and engineering feat, regardless of the science that we do with it, which is the real reason I'm interested in it. This is the ATLAS detector. It's quite big. The bits that Lancaster built are actually buried way in the heart of it here for the tracking. We also did a lot of work on the computing system that's required to analyze all the data coming out of there. I help manage quite a lot of that, and I run it for the UK. But just to give you the scale, those two little objects at the bottom are people. This is the program that draws this is called Géant. This is the Géant Standard Man. This is the Géant Standard Woman. So, antimatter comes into this because half of all of the particles that we produce in those collisions are antiparticles. They're antimatter. In fact, in almost every physics process we have ever encountered, matter and antimatter are treated completely equally, which poses a problem that we'll come back to. Well, let's just go back to some of the science fiction ideas for a moment. This idea that you could accumulate the antimatter at CERN, steal it and turn it into a bomb. Is that plausible? Well, according to Angels and Demons, they managed to steal 0.5 gram of it. So if we could actually make 0.5 gram of it and put it into a container and transport it safely to another state, we could indeed make a bomb that's about as powerful as Angels and Demons. 1 gram of antimatter annihilating would release about 3 times the energy of the bomb that was dropped on Hiroshima, which was 40 kilotons of TNT. And that's the equivalent of about 50 hours of output from Hisham power station. Okay, so it's a lot of energy. But is this plausible? I mean, am I being really reckless making all this antimatter? Well, no. All of the antimatter that's produced in our experiment annihilates within a fraction of a second. And how much energy does it release? Well, we actually had Tom Hanks came to visit us, and he said, how much antimatter would you need to annihilate to warm his mug of coffee? And the answer is, if all the antimatter produced in our experiment were put into Tom Hanks's cup, it would raise the temperature about 1 degree centigrade per hour of operation. It's a really, really low rate of energy release. To put that in contrast, that coffee cup just left standing around would have cooled by 10 degrees over an hour just by normal cooling. So this wouldn't even keep it hot. You'd have to do a lot better than that to even keep it warm. How long would it take for you to accumulate 0.5 gram? Well, if we took all of the antimatter we produced, it would take about 10 million years to get 0.5 gram. So I don't actually think we're going to be threatening the Catholic Church or any other religion of your choice in the near future. In a real facility that we have at CERN, which you may have heard stories about recently, they are trying to accumulate antimatter, tiny amounts, because it's really difficult. But what they're trying to do is trap antiprotons and anti-electrons in a magnetic trap, because as soon as this stuff gets near any ordinary matter, it will annihilate. So you need to keep it away from everything else. So you use magnets to manipulate it to keep it away from everything else. And then you try and put your antiproton and your anti-electron together and make an anti-hydrogen atom. And the reason that we're doing that is to see whether the anti-hydrogen behaves in exactly the same way as you would expect from a hydrogen atom, to see whether there are in fact any differences between the antimatter version of things and the matter version of things. And the reason that we really want to understand that, I'll come back to in a minute. But if you use that facility, Athena, to accumulate this, then it would take 1,000 million years to capture 1 gram. So 500 million years to capture your 0.5 gram. What about antimatter in everyday life? I mean, I'm trying to tell you that this stuff is real. Well, it is. And it is used in about 40 hospitals, for instance, around the UK. This is something that was developed at CERN, but is used in pretty regular medical treatment. And I hope you don't need it, but I hope you'll be grateful to it if you do need it. There's a thing called a PET scanner, a positron emission tomography scanner. Remember, positron, that's an anti-electron. If you make nuclei, radionuclei artificially, you can make some of them which will actually decay and emit antiparticles. They'll emit anti-electrons, positrons. And you can put those radionuclei into tracers that you can deliver very specifically into parts of people's bodies. And when the positron is emitted, it almost immediately finds an electron, which it annihilates with, and gives a very characteristic pair of hard photons, hard particles of light, that you can detect, and by backtracking them you can see exactly where they came from. So you can work out the distribution of these annihilations, so you can trace exactly where in the body these annihilations are happening, and you can use that to image little structures within the body that are taken up by whatever tracer that you put in. That's really useful and is being used practically every day. Actually, there's antimatter in this room even now. This is a rather strange statement, but if you work it out quantum mechanically, about 15% of you and me at any given time is made up of antimatter. The reason that it doesn't matter is because that antimatter is created and annihilated almost instantly. This is a consequence, goes back to that uncertainty principle that I talked about before. Because of the uncertainty principle, even in empty space, you get particles and antiparticles suddenly coming into existence and then destroying themselves all the time. The vacuum turns out to be a very complicated thing, and it's completely full of activity. Empty space is full of activity. There is evidence for that which has been known since the 1950s. It's called the Casimir effect. Because even in a vacuum, these particle pairs are being created and destroyed. And you can take two plates of metal and measure the force between them. If it's in a pure vacuum, you'd expect there to be no forces between them. If there's no charge on the two plates, there should be no forces acting between them. But you find that there is a measurable force acting between them, and that's because of charged particle-antiparticle pairs being created in the space between them, which suddenly are attracted towards the conductor, the metals, and they actually end up polarizing and pulling those two plates together. Now, one day, someone's going to be smart enough to harness that effect. Feynman thought about it for a very long time. At the moment, nobody's done it, but potentially there is a source of energy there in free space that we could access, and it's really there. Okay, now, back to that problem that I mentioned. Remember I said that basically every process we know produces matter and antimatter in equal amounts and treats antimatter and matter equally, even-handedly. Well, we know that the universe, we believe the universe, we know it came from a very hot, dense state. We came from something that we call the Big Bang. The precise details of the initial state, let's leave for now. We know there was a Big Bang, which was where all of the matter came from. But hold on, those physics processes we know produce matter and antimatter equally. Well, there's not obviously a load of antimatter around you now. I mentioned that there's some little fluctuations going on, but we are clearly predominantly just in a matter state. Where did the antimatter go? Because if I do my experiments in Atlas, I produce matter and antimatter in equal amounts. So the early universe will have done the same. Something happened that took the antimatter away. Something is distinguishing between the two. Are we just really lucky? Maybe there was some just fluke. Are we just being really lucky and we didn't go tip over and they just happened to fluctuate by some random process to be a bit more matter than antimatter, and that's why we're here? Well, it's not just lucky like that. It's lucky like that. We are really, really exceptional if we really would have to have fluctuated hugely. The matter and antimatter in the universe should have annihilated a long, long time ago. And this universe, according to what we know, should be a rather unpleasant place, mainly full of high-energy gamma rays, high-energy photons. But we do exist, so clearly something else happened. Just to illustrate this again, this is the rate at which matter and antimatter must have been produced in the early universe, and that's 10 billion and 1 parts of matter to 10 billion parts antimatter, if you're just going to try and explain the universe that we live in, and that's us that's left. So most of what was created has gone away. But what allowed that imbalance to happen? Well, we do know of one process that we've seen, we've known since the 1960s, a type of radioactive decay that slightly favors matter over antimatter. But it's about 1/10,000,000th of the strength of the effect that you would need to describe the world that we live in. So you may have heard about some of the stuff that we do at Atlas, like the Higgs boson. If we've got time, I can come to some of that later on, if you want to ask about it. But one of the things that in Lancaster we're particularly interested in measuring is looking for effects that distinguish between matter and antimatter. most of the particles, that most of you and me, is made up of little objects called quarks. We're mainly made up of what's called up and down quarks, which are relatively light. There's some other types of quarks which are much heavier. The B quark is something of order, let's get this right, about 15 times heavier than the up and down quarks that you and I are mainly made up of. So we can make them fleetingly in our collisions. There's an even heavier one, which is something like 1,500 times heavier. That's the top quark. But that doesn't make nice stable particles, so you can't do the nice experiments with it. So what we look for are things like particles. They're called beauty particles. It's this B here. And the particles that are made up, we call the big B-Meson, which actually contains an anti-B quark with another type of quark called a strange quark. And that can then decay into an object called a J psi and another object called a phi. Now, interestingly, you can flip everything in that diagram and exchange that for a B quark, not a B antiquark, and that for an anti-strange quark. You can change the sign of that. You can make that an anti-C quark, make that an ordinary S quark, that's an anti-S quark, that's a C quark. What you end up with is exactly the same final state. So you can have the anti-B-Meson and the B-Meson both decay to the same final state. The nice thing about that is we can look at our decays that look like that go to that final state, and we can look for differences between the way the antiparticle decays and the way the particle decays. And we can do that and try and establish if there are other effects which are giving you more of an imbalance, more of a favouring of matter over antimatter to answer this big question of how we happen to be here. Now, there are some other nice features. That J psi is very easy to identify, and it also turns out to be a very useful object to study in its own right, not least because we had to understand that J psi to understand the measurements we were making to discover the Higgs boson. So we actually help other things. There are also some other quite cute things going on here. I talk about matter and antimatter. There are some rather strange effects that you can find with antimatter and antimatter. There are some of these particles, these beauty particles, have the rather strange ability through a quantum mechanical effect called a loop diagram. This is a loop of other particles, where it can turn from a particle into its own antiparticle. And here's another example of something going from the particle into the antiparticle. That actually in physics turns out to be a really nice situation, because you can look at the interferences that go on between these things and make really, really precise measurements. So it's quite beautiful. But also, it gives me the excuse of finding young people on the front row who might like a sweet, because I have some rather interesting sweets I discovered here. I don't know, was anybody here for Laura Kormos's talk in the physics series last year where she was handing out ice cream? Yeah. Well, remember they were talking about mixing the ice cream and getting different flavors of neutrino? That's a similar thing to this oscillation between particles and antiparticles. These sweets I've discovered are really weird. You chew them, they start off with one flavor, you keep chewing them and they change to a different flavor. They change from orange to strawberry or lemon to orange and things like that. Quite weird. Anyway, cheap bit of theatrics, but if anybody else wants one of these, they can have one. Yeah, bribe the audience, it always works. Oh, there's people on the front row, have some sweets.
Thank you.
Sorry, Roger, am I interrupting you?
No, you go ahead. I'm about done anyway.
You want to do a bit of dancing around here, don't you?
Okay.
I'll tell you what, do you want any more of these?
Oh no, we're fine, go on. I've got another bag.
There you go.
You're only depriving my first year students who I bribe with those anyway. Okay, there are some other things. This is where I'm getting sort of into the technical stuff that we actually do, but I think I should tell you about it. There are some other interesting things about matter and antimatter. A lot of the particles that we deal with are actually a quark and its antiquark bound together into a system called a meson. And interestingly, there's a lot of very interesting mesons which are the same sort of quark and its antiquark. So a beauty quark with a beauty antiquark bound together, or a charm quark with a charm antiquark bound together. Now, you're probably saying, hold on, that's matter and antimatter, won't they annihilate each other? The answer is yes, they will. But it takes a little while for it to happen, and there are some interesting bits of physics that stop it happening immediately. But while they're hanging around near each other, they have some interesting properties. It turns out to be a really interesting laboratory to study the forces which are binding them together. Those forces are the forces that hold your nucleus together in your atoms. They're the forces that actually are responsible for most of the mass of most objects that you look at. I know we bang on about the Higgs, which gives mass to the fundamental particles. But beyond that, most of the mass that you're measuring is actually due to the strong force binding those fundamental particles together. And we can really learn about how that strong force works by studying these systems where we've got quarks and their own antiquarks bound together closely. So we study these things which are called onia. And actually in those studies, we actually discovered the first of the new particles at the LHC. We found a thing with a really sexy name of the Chi-B3P. I was on radio saying that so often, you really can stumble over that quite easily. But it's kind of interesting. It was something that people working on the strong interaction said should have been there about 30 years ago. Lots of experiments were looking at it, should have been able to find it, but they didn't. We looked at it in Atlas, and this bump here and this bump here below are a very clear signature for that new particle, which shows that our theory of the strong interaction is pretty good. This thing was sitting at the right place with about the right strength, and we were the first people to find it, which is nice. So this was quite a nice bit of measurement. So this is just to relate my work to some of the work of the other people in my group. So within my group, there's another experiment called T2K, which Laura Kormos, who I mentioned before, works on. They're looking at the relationship between different sorts of neutrinos in a very different sort of experiment. So they have a source of the neutrinos over here on one side of Japan, a place called Tokai, and they fire them almost 300 kilometers through Japan, and they have a detector sitting away at a place called Kamioka. This is a big, huge detector full of water called Super Kamiokande. And what they're looking at, they fire a type of neutrino called an electron neutrino from here, and they look at what they can actually measure over here. And they were the first people to prove that electron neutrino beams, by the time they get over here, you find a significant amount of muon neutrino in there, which is a pretty important discovery. The interesting thing about that is that same sort of oscillation between one type of neutrino and another is another place where you could see a signal of physics which is biased against antimatter and in favor of matter. So both of our experiment groups are looking at this question of what is it that favors matter over antimatter. How long have I got?
Well, you've got 10 minutes really.
Okay, because that essentially was the end of the matter-antimatter part. I just thought I'd say a few more words about some of the other stuff we're doing in the Atlas experiment. So we're looking at far more than just matter and antimatter, of course. So I thought I'd mention a couple of the other things. So there's another big universal question that really needs answering, and that is, what is the universe made of? Because the stuff of you and me, the stuff of stars, the stuff of stellar dust, the stuff of black holes, makes up about 4% of the gravitational mass of the universe from our astronomical observations. By various means, we know that there's another 23% or so, which is something else, which behaves like matter, but isn't protons and neutrons and stuff like you and me. It's what you may have heard of as dark matter. It's not radiating, it doesn't shine, it's basically, it isn't charged, it's this dark matter. And then beyond that, there's an even bigger mystery, because there's another 72, 73% of the gravitation is due to something which doesn't even behave like matter. It behaves like a field of energy, and that people call dark energy. And that we really struggle to understand what it is. This is really embarrassing for me as a scientist and as a physicist, when we think about it, that 4% of the universe, I can tell you what it's made of. And something like 1/5 of what's in this room right now, I know what it is. There's another 4/5, which is something I don't know what it is. It's matter, but I don't know what it is. And I can walk through it and not even notice it. It's only when I look at the astronomical scale that I detect that it's there. This is a real mystery. Now, you can tell that this is going on because if you look at the visible mass in things like rotating spiral galaxies, you know what it takes to hold them together, you know how much gravity it takes, and you know how much mass you can see there, how much ordinary matter you can see there, and there's more needed than you can see. So you know there has to be dark matter. Also, you can look at the separation of dark matter into ordinary matter in the collisions of two clusters of galaxies. And you can actually even measure the distribution of the dark matter in those galaxies. So what is it? It fills the space, but we barely interact with it. Well, we have ideas. We don't know, frankly, but we do have ideas. One of the ideas is a class of particles that we've been talking about in particle physics to explain a lot of problems, called supersymmetric particles. And these would be made in great abundance in the very early universe, in the Big Bang. Both supersymmetric particles and supersymmetric antiparticles, I hasten to add, just to bring it back to the antimatter thing. Now, if the constituents of matter, of the dark matter, are new particles like that, and if they're at the right energy scale, we should be able to discover them. And in fact, for most supersymmetric theories that we know of would predict that somewhere within the range of the Atlas experiment, when we upgrade to the new energies, we would hope to be able to see them. And we could make these particles directly, because effectively by banging these protons together at really high energy, we're reproducing in a very small volume of space some of the conditions very close to the start of the Big Bang when these dark matter particles would have been produced. So we can look for them directly there. And it could be other things. There are other theories. There are axions and things like that which have been proposed. Again, we should be able to make them if we have the right energy there. Okay. And the Lancaster group is certainly looking for evidence of supersymmetry and lots of different sorts of new physics. Even that J-psi decay that I mentioned before is actually sensitive to new physics beyond the energy scale that the detector can, the experiment can make. Because remember I had those little loops in some of those diagrams? Weirdly in quantum mechanics you can put objects which are too massive for you to make directly for a very brief instant into those loops. And it changes the processes that come out and it makes you sensitive to particles beyond your normal range of accessibility. It's a very clever little way of looking beyond where you think you have the ability to do. Okay. And of course, I think I have to say something about the Higgs boson. You know, we just had a Nobel Prize announcement. We all went a bit silly on that, so I have to mention it. So this is the so-called God particle, which actually was originally that goddamn particle. As Leon Lederman called it. He actually wanted his book to be called The Goddamn Particle, and he was told by his publisher that you can't use profanities in the title of your book. But the word God sells, so the publisher changed the title to The God Particle. So this is being studied by Atlas. I can do God in 5 minutes, come on. I did quantum mechanics in one slide. Okay. What is mass? It's all about mass. In our theories, we have a beautiful theory of all of the interactions between the subatomic particles. And it works beautifully. We've tested it now for almost 40 years, and it's come through every test with flying colours. The standard model of particle physics really works. It's just got one slightly embarrassing feature. It only works because of the symmetries. I always bring symmetries into my talk. That were there in the standard model. And those symmetries are completely broken if any of the particles have a mass, which is kind of embarrassing because clearly the particles have masses. What's a mass? A mass is, in essence, it's the resistance to motion. That's probably the easiest way to explain it. If you've got a very massive object and you apply a certain force, it won't move very much. If you've got a less massive object and you apply the same force, it'll move, it'll accelerate quite quickly. That's the basic idea of what a mass is. Okay? These particles have masses. So people struggled for a long time to explain how these particles could have a mass, and yet we don't break all of the symmetries. And this is the problem. What makes these particle masses and what makes them so different? So Peter Higgs and Englert and sadly dead now Brett came out with a theory which was quite smart. It said, look, maybe the particles really are massless. But If you have a universal field that you can interact with, and if it's everywhere, these particles, as they travel along, they can interact with that field. When you interact with something, there's energy involved. And like you remember from before, E equals mc squared, that energy corresponds to a mass. So the particles appear to have a mass because they're interacting with this field. But we haven't broken all of the symmetries that we need to make the theories work. Neat idea. Okay, but where's the evidence? Well, in an idle moment in 1966, Peter Higgs was told by his editor, there's nothing much new in this paper. What can you tell me that's new? And he said, well, if there's a field, I suppose there has to be a quantum associated field with the field. There has to be a particle. Oh, great, we can go and look for that. This is why we call it the Higgs field and the Higgs boson, because he was the one to point out that there's a particle to look for associated with this field. So we went and looked. The only problem was we didn't know how massive that particle would be. So we didn't know what energy to look for. We knew sort of how it would behave, but that all changed depending on how heavy it was. And it took us until the 4th of July 2012, before in Atlas and in CMS, we had enough evidence that particle really exists. And that's the Higgs boson, which is definitely worthy of a bottle of champagne. And I'm afraid I ate my chocolate Nobel Prize because they didn't send me a real one. But we were mentioned in the citation. How does it work? Well, this is one of the classic arguments. I've got a little demonstration actually in my bag, which is quite fun, but I think it doesn't really work in a big room like this, and certainly not with the lights out. But maybe some people can see this in questions afterwards. But with the Higgs, you've got a whole crowded room of people. Imagine it this way. And they're just talking away. And then a certain famous physicist walks into the room. What happens? People can mill around pretty well in that, but he has a cluster of admirers, and they all gather around him, and suddenly he finds it really hard to move. He's interacting with that field of people around him, and because of that interaction, he finds it difficult to move. He appears to have more inertia. He appears to be heavier, more massive. That's the analogy. That's kind of how it's supposed to work. So we went away and we looked for the signatures of the particles, and this is a display of one of the Higgs candidates that we saw in the Atlas experiment. It's quite complicated how it's produced. It decays into two very massive objects that we've known since the early 1980s, which also won a Nobel Prize, the discovery of the Z particles. There's two Z particles, and they decay into two other particles called muons, and they're actually really easy to detect, so it's a nice clean signature to look for. And here we can see, if you see just the red lines here, these are the four muons coming out. And if you put those together, they look like they come from an object which has got 125 GeV mass. That's the units we use to measure the mass of particles in particle physics. In Lancaster, we're looking at a slightly more challenging mode. We're looking at something which is supposed to happen a lot, a Higgs decaying to 2 tau leptons, which is a heavier version of the muons, which are in turn heavy versions of the electrons. But these should be there. And I can't tell you whether we've seen them or not. I know whether we've seen them, but I can't tell you because it's not public yet. But make of that what you will. But, you know, we have certainly seen the Higgs in other modes. And here we are sitting in a big conference in Australia as it was announced. This is the spokesman of the Atlas experiment. And this is me just ligging immediately behind. I'm always there to donut people at big events. So that we've really got the Higgs, so that means we have to make sure that all of the properties match. One of the unique properties of the Higgs is that unlike all of the other particles I mentioned, it doesn't have this little quantum mechanical version of spinning around. It's a spinless object. And actually, that seems to be the case from what we've seen so far. It also should decay into many different sorts of objects at exactly the predicted rates. So we're concentrating on the Higgs to the taus. And the other very important thing is there should be only one Higgs. But there are many theories that say, no, this could be one of a family of Higgs. Those supersymmetric theories I mentioned would predict whole families of Higgses, which could be more massive, and therefore they're harder to see, they take longer. So we've got to look for those, and that's what we're looking for. I probably haven't got time to show you these things. These are nice little animated graphics that can show how our signal built up over time. But I'll skip over that. Another thing that we're looking at in maybe the last minute or so is we're looking for other dimensions, which sounds really like I've gone back to talking about science fiction again. But I haven't, because almost all of the theories that try to go beyond what we currently know in particle physics suggest that there are not just 3 dimensions of space and 1 dimension of time. There appear to be other space-like dimensions, but they are not acting like the 3 dimensions that we know. They are what is known in theory as compactified. They are almost kind of rolled up. And the way they express themselves is through the forces that we see, like gravity, like electromagnetism. They're a way of, if you like, geometrically trying to explain how those forces work. Because we understand how gravity works as part of the geometry of space and time since Einstein. That's what general relativity is about. These are extending that idea to try and explain the other forces we know about, also in terms of the geometry, but it means we have to add extra dimensions to the space and time. And so we're looking for that. One of the signatures would be the production of micro black holes, but this might also explain why the force of gravity, which seems big to us, but is actually really weak compared to electromagnetism. Why is that? If you don't believe me that gravity is really weak compared to electromagnetism, think of it this way. If you have a little piece of metal and you have a tiny little bar magnet, you can do a tug of war between that magnet and the Earth. And if you pick it, you can pick up the piece of metal with your bar magnet. The bar magnet wins. The thing the size of the Earth, which is trying to fight it with gravity, loses. Gravity is really weak compared to electromagnetism. Okay, and the other thing we're looking for is the unknown. The ATLAS experiment is bringing physics into completely new territories. The really exciting discoveries would be the completely unknown things. New processes, new particles, new forces could change our whole idea about the reactions between energy and matter and antimatter, and also give us a new understanding of how space and time work. So we'll learn more, we hope, about the basic forces that shaped our universe since the Big Bang, and it will determine its ultimate fate as well, because it's the same rules running all the way through. So the future is ahead of us. What's the matter with antimatter? Well, frankly, we know the problem, but we don't know the solution, and we're working on it. The discovery of the Higgs boson was a really big moment for the experiment. It was quite exciting for us all, but many questions remain to be answered. And if you're young and you're interested, why not think about joining us? Because this stuff isn't rocket science, it's particle physics. And particle physics, if you put the work in, you can do it. I'm not that clever, but I find this stuff really interesting. So that's basically it, apart from one advert, which explains the strange thing growing on my top lip. We have a team called the Higgs Boson, which is part of the Movember charitable event. And this is my contribution, which I stress only started on Saturday. I was a late starter. All right, thank you very much.